Geometric applications of rates of change. Hello everyone. To begin, let's recall what we have covered in our previous lessons. We established that, at its core, a derivative represents the rate at which one quantity changes in relation to another. Now, we are going to apply this fundamental concept to the field of geometry. In geometric problems, we frequently encounter scenarios where the physical dimensions of a shape, for instance, the radius of a circle or the length of a side of a cube, are not static, but are actually changing as time passes. It is important to realize that when these primary dimensions change, they trigger a ripple effect. Consequently, other geometric properties, such as the total area, the volume, or the perimeter of the shape, will also change. Therefore, the primary objective of this subsection is to teach you how to use the tools of calculus to calculate the instantaneous rate of change for these specific geometric properties. In the following slides, we will walk through a systematic, step-by-step approach to solving these problems and examine some real-world examples to solidify your understanding. Systematic approach to solving problems. Now that we understand the concept of how geometric properties change over time, let's look at a systematic approach to solving these problems. To find the rate of change of any geometric quantity, we will follow a structured three-step process. First, step 1 is to establish the geometric formula. Before we can apply any calculus, we must identify the mathematical relationship between the variables involved. You should always start with the standard formula for the specific property you are analyzing. For example, if you are working with the area of a circle, you would use the formula A equals pi r squared. Similarly, if you are analyzing the volume of a sphere, you would use V equals 4/3 pi r cubed. Once you have your formula, we move to step 2, differentiate with respect to time. In these problems, dimensions like the radius or the side length are not constant. They change as time passes. Therefore, we differentiate the formula with respect to time, denoted as t because these dimensions are themselves functions of time. We must apply the chain rule. To illustrate this, if we take the area of a circle, A equals pi r squared, the derivative of A with respect to t is equal to the derivative of A with respect to r. Multiplied by the derivative of r with respect to t, this simplifies to 2 pi r times dr over dt. Finally, we reach step 3. Substitute instantaneous values. It is crucial that you only do this after the differentiation is complete. Once you have the derivative equation, you can substitute the specific values given for the dimensions and the known rate of change to solve for the unknown rate. By following these 3 steps, formula, differentiation, and substitution, you can solve any rate of change problem consistently. In the next slide, we will apply this exact process to a real-world example involving an inflating spherical balloon. Real-world example: the inflating spherical balloon. Now that we have established the systematic 3-step approach in the previous slide, let us apply it to a practical example involving an inflating spherical balloon. The problem states that the volume of the balloon is increasing at a constant rate of 100 cubic centimeters per second. Our objective is to determine the rate at which the radius is increasing at the specific moment when the radius is 5 centimeters. Let us proceed using the structured method we just learned. First, we identify the geometric formula. Since we are dealing with a sphere, we use the standard formula for volume, where V equals 4/3 pi times the radius cubed. Second, we differentiate this formula with respect to time, t as we mentioned in our systematic approach. Because the radius is a function of time, we must apply the chain rule. The derivative of volume with respect to time, written as dv over dt, is equal to the derivative of 4/3 pi r cubed. When we differentiate the radius cubed, we bring down the exponent of 3, which cancels out the 3 in the denominator. We then multiply by the derivative of the radius with respect to time, written as dr over dt. This simplifies our expression to dv over dt equals 4 pi r squared times dr over dt. Finally, we substitute the given instantaneous values into our differentiated equation. We are given that the rate of change of volume, d, v over dt, is 100 cubic centimeters per second, and the radius, r, is 5 centimeters. Substituting these values, we get 100 equals 4 pi times 5 squared times dr over d. T, since 5 squared is 25, the equation becomes 100 equals 4 pi times 25 times dr over dt, which further simplifies to 100 equals 100 pi times dr over dt. To solve for the rate of change of the radius, we divide both sides by 100 pi. This gives us dr over dt equals 100 divided by 100 pi, which simplifies to 1 over pi centimeters per second. Our final answer is that the radius is increasing at a rate of 1 over pi centimeters per second. Pay close attention to how we differentiated before substituting the value of the radius. This is a critical point that we will revisit when we discuss common mistakes in a few slides. For now, let us see how this same logic applies to a different shape in the next example. Real-world example, the expanding metal cube. Now that we have seen how to apply this process to a sphere, let us look at another example involving a different geometric shape, a metal cube. Imagine a metal cube that is being heated. This heat causes the metal to expand, meaning the side length of the cube is increasing at a constant rate of 0.1 centimeters per second. Our objective is to find the rate at which the volume of the cube is increasing at the specific moment when the side length is 10 centimeters. To solve this, we will follow the same systematic three-step approach we established in the previous slides. Step 1 is to identify the geometric formula. For a cube where the side length is represented by the volume V is calculated as the side length cubed, so our formula is V equals a cubed. Step 2 is to differentiate this formula with respect to time, t. Because the side length is a function of time, we must apply the chain rule. The rate of change of volume with respect to time, denoted as d, V over dt, is equal to the derivative of volume with respect to the side length, multiplied by the rate of change of the side length with respect to time, which is d, a over d, t. When we differentiate a cubed, we get 3a squared. Therefore, our differentiated equation is d, v over dt equals 3a squared times d, a over dt. Step 3 is to substitute the given instantaneous values into our equation. We are given that the rate of change of the side, d, a over dt, is 0.1 centimeters per second, and the side length, at this instant, is 10 centimeters. Substituting these values, we get d, v over dt equals 3 times 10 squared times 0.1. This simplifies to 3 times 100 times 0.1, which results in 30 cubic centimeters per second. Our final answer is that the volume of the cube is increasing at a rate of 30 cubic centimeters per second. As we move forward to the next slide, pay close attention to the order of these steps, as substituting values too early is a common mistake we will discuss shortly. Common mistakes to avoid. Now that we have walked through the practical examples of the inflating balloon and the expanding metal cube, let's discuss some common pitfalls. It is important to be aware of these mistakes to ensure your calculations are accurate and your logic is sound. First, let's address the issue of forgetting the chain rule. A very common error I see is when students differentiate the area of a circle, area equals pi r squared, and simply state that the rate of change of area with respect to time is 2 pi r. You must remember that since the radius is a function of time, you cannot stop there. You must multiply by the rate of change of the radius with respect to time, which is written as dr over dt. Without this term, you are not accounting for how the radius itself is changing over time. Next, please be mindful of your units. It is easy to overlook this, but consistency is vital for a complete answer. When you are dealing with volume rates, your units should be in cubic units per unit of time, such as cubic centimeters per second. For area rates, you should use square units per unit of time, like square centimeters per second. And for linear rates, such as the change in radius or side length, the units are simply units per unit of time, for example, centimeters per second. Finally, avoid the temptation of substituting your instantaneous values too early. For instance, in our previous balloon example, you might be tempted to plug in 5 centimeters for the radius into the formula before you differentiate. However, if you do this, the radius becomes a constant number, and as we know, the derivative of a constant is 0. This would lead you to an incorrect result. Always follow the systematic approach we established. First, identify the formula, then differentiate to find the general rate of change, and only then substitute the specific values for that instant. Keep these 3 warnings in mind as we move toward our final key takeaways in the next slide. Key takeaways. Now that we have walked through the practical examples and identified the common pitfalls to avoid, let us conclude this lesson by reviewing the key takeaways. First, let's recap the core concept. Geometric rate of change is the application of derivatives to determine how one property of a shape, such as its area or volume, changes as another property, like its radius or side length, changes over time. To ensure accuracy in your calculations, always adhere to the systematic 3-step process we established. Begin by identifying the correct geometric formula, proceed to differentiate that formula using the chain rule, and only then substitute the given instantaneous values. This brings us to the most critical technical point, the chain rule. It is essential to remember that the rate of change of a property with respect to time is equal to the rate of change of that property with respect to its dimension, multiplied by the rate of change of that dimension with respect to time. Finally, always interpret the sign of your result to understand the physical behavior of the object. A positive result indicates that the property is increasing, while a negative result indicates that the property is decreasing.